All right, well, good evening and welcome to lecture 21 for MT225. Um, so we're past the high point, I suppose, in the class. It's kind of downhill coast from here. We've done the most difficult material that we've got. Um, and so since we do have a relatively limited amount of time remaining in the class, I've kind of laid out in our administrivia slide here our schedule for the remainder of the semester. It's reasonably easy to predict at this point. Um, exam two has been returned, so those of you who submitted exam two to me, you got email from me yesterday about that. So check your student email. I've been sending everything to the student email addresses since those seem to be the ones that I have at least guaranteed delivery on. You can set those up to forward to Gmail or to any other kind of account you use if you don't like to log into MV's system to check it. But those are the ones that I have to use for official communications. So exam two has been returned and homework eight's been returned. Results on both were pretty good. We had pretty solid results on exam two. For the most part, I mostly saw just simple mistakes, forgetting an arm here or missing a moment there, a couple sign issues here and there, things like that. There weren't too many submissions where it was pretty clear there was no clue. Uh, all of you looked like you had a pretty good idea of what you were doing. So also homework 8 has been returned as well. So our schedule, the remaining time that we have left, we basically have 3 weeks left in the class, taking into account the fact that we have worked through spring break. So even though we got that extended spring break, we got that 1 week, um, we have already, uh, we spent an extra week. So we're right about where we need to be. Um, the way the schedule works here for this week, our topics for the 13th and 15th will be stress and strain. We'll be looking at materials science in the next several sessions. We're looking at materials and how we design materials to be used in a particular structure or system. It starts with truss analysis, for example, or equilibrium analysis. We figure out what the loads are on each part of the structure. Then we have to ask, well, what material can I use to support that load? That's what we'll start to figure out tonight. Um, next week, we will have the our section a little bit more on materials, material properties, and bending and deflection of beams. So we'll look at things like I-beams, for example, and figure out, based on how we're supporting them and where we put loads, how much they deflect, how much they move. Pretty important ideas in a lot of different structures. Uh, we'll also have homework 9 due. I'll be issuing homework 9 on Wednesday on stress and strain. That'll be our next to last homework assignment. Our last week of class is 427 and 429. I think that's right. Double check my dates on that. I think 427 is, yeah, that's a Monday. So the 427 will be our final exam review night. So any problems, questions going back to the beginning of the class, uh, those will be what we'll be able to review that night. I will post sometime during next week. I'll post a sample final exam so you can get some idea of what that'll look like. But it is cumulative. It does cover everything that we've done this semester. And then 429, our last night of class, we will have our final exam. There will be a bonus homework assignment covering materials and bending of beams, similar to all the other bonus assignments we've done. It's not required, but it's a good idea to do just for practice for the exam, because the material on that will be covered. But that'll be it. So 429, we'll do our final. I'll grade those as quickly as I can, and we'll get you your grades out hopefully first week of May. Anyone have any questions on the schedule? All right, so let's look at what we're doing tonight. So we're looking at the introduction to strength of materials. So the strength of materials, moves us away from using the ideal materials that we've considered at this point. Back when we started into trusses, I mentioned that all the truss members were made out of unobtainium, which is a material that has infinite properties in every direction we'd want, has infinite strength, infinite rigidity, doesn't change shape and size. Real materials have limits to them. Real materials have spring behavior. They change shape when you apply forces to them. So we have to take that into account. What we'll learn how to do tonight is evaluate what we call stress. Stress and strain in materials are about how materials, real materials, respond to load. There's always an application of a load and then a response to a load. Think about applying a force to a spring. You apply a force to a spring, that spring expands or contracts in response to that force. We have the same kind of behavior in a beam of material, and we have to learn how to evaluate that. And we'll take a look at what those principles are here. Those of you who have already been through things like sheet metal will recognize a number of the concepts that we'll see here. So we're going to be looking tonight at what we call normal stress and normal strain, and I'll define what the word normal means here in a moment. On Wednesday, we'll look at what we call shear stress and shear strain. So stress and strain, we've got to start with some definitions first. What the principle of stress is. We'll come to strain later, but stress is the most important concept that we have to take a look at tonight. And if we put ourselves in context here, we are looking at what we've just come off of, solving truss problems. In solving a truss problem, we found out what forces were carried by each of the structural members. We found out how many pounds or how many kips of force were carried and what the direction was, whether it was tension or compression. But we never really bothered thinking whether or not the materials could actually support that load. We just did the calculation, said, okay, this member carries 2,300 kips in tension. Well, 2,300 kips is 2.3 million pounds. That's a lot of force, and we have to be concerned about whether that's going to actually be able to handle that load. That's what the strength of materials will buy us, the ability to design and figure out what materials we need and what dimensions we need, how big or small these things are that we can get away with. Shape didn't matter in doing truss analysis. It didn't matter whether we used a round beam or a rectangular beam or an angle bracket. The shape didn't make any difference because the material had infinite properties. We considered it to be essentially as small as we'd ever need it to be. In fact, we draw it out on most of our drawings. We drew it out as straight lines, just very thin lines. Real materials have to have some dimension to them, have to have some size, some thickness, and that plays a pretty big role in terms of stress and loading. So the way that people have figured out to look at these concepts is to focus on the material. Essentially, I like to think about it as zooming in on the material so far that you lose the picture of what the structure actually is, and you're really looking at the forces at the molecular level. That's essentially what stress is. Stress is a force inside the material that occurs between the bonds that make up the material, or between the grains that make up the material, if you're more familiar with materials on that kind of concept. So we have to jump inside the material and look at what's going on at that level. That helps us to simplify things quite a bit because, as we'll see in a little bit, otherwise we'd need to have reference information for every possible size and shape of materials out there. The way that people have learned how to deal with materials is to ignore, or at least find a way to factor out, the shape and instead focus on what the internal forces are. And that buys us a lot of simplification, which we'll see here in a bit. So let's look at the picture here. What's drawn on the screen is a single member of a truss. It's a rectangular member, and it's got some force on it. Let's say it's got 20 kips on it. It's got 20 kips in tension. So it's being pulled with 20 kips of force in each direction. We've got 20 kips of force on the left, we've got a 20 kips on the other side to counteract that and keep it in equilibrium. So that might be what the free body diagram would look like with each arrow labeled 20 kips. 20 kips to the left on one end, 20 kips to the right on the other, keeps it in equilibrium, but that means that the member has a force of 20 kips on it, and it's 20 kips in tension. What we want to do is look at what's going on in the beam itself. So we're looking at what's happening inside. We've looked at things mostly externally. When we looked at method of joints, we looked at what the forces were essentially on the ends of the beam. Method of sections, we cut through the beam. And essentially that's what we're going to do here. We're sort of modifying method of sections. If I were to cut through this beam and ignore the right-hand side, take some sort of magic chainsaw or something and cut through the middle of this beam. If I did that without applying any forces, I cut through the middle of that, I think you all could imagine what's going to happen with this beam. If I cut through the middle of it and did nothing else, this thing's going to separate. The right side's going to shoot off to the right, the left side's going to shoot off to the left. We'll no longer have equilibrium. But if we cut through that member, at the exact second we cut through that member, we grab on to, let's say, the left side and apply exactly the right amount of force to keep that piece in equilibrium, what we're doing is we're exposing what force the right side of this member must have been exerting on the left. That's exactly what we did in method of sections. But now we're going to look at it a little more closely. We're going to zoom in on it. That's what's shown on the next page here. If I zoom way in on the left side of that beam after I've cut it, what we find is that the forces in the beam are not hooked on to one point. They're distributed, they're spread out. So if I zoom way in, I've got some area here. I've got some cross-sectional area that this member has. Let's say, for example, it's a rectangular beam, and I'll go ahead and draw it on my sheet here, and we can transition over to that here in a moment. So let's see here. There we go. All right, so let's see. Why isn't my video showing up? One second here. Something's not right. I'm not getting my display up here. See Mark's name though. Oh, here we go. Technical difficulties. There we are. All right.
As long as you got my name, you're fine.
Yeah, there we go. So here's this member that we've just cut through. We've got 20 kips of force there. When you cut through one of these, you're not thinking about it anymore as just a single line that is infinitesimally small. It's got some area to it. If I were to cut through this and view the end I cut, here I'll draw an end view. It's going to be some rectangular shape. So let's say this is maybe a piece of wood or something like that, like a 4x4 or something. We've got a rectangular cross section. The force that we need to apply on this end that we've cut has to add up to 20 kips. Otherwise, this thing won't be in equilibrium. But the force isn't applied at a single point. That force is spread out over this area. So it's drawn in the notes looking something like that. What it really is we'd see little dots. If you imagine these dots are the heads of the arrows that we're seeing here, every square inch of area has some amount of force on it. Now, that does get a little complex down here at the end. And for our purposes in this class, we have to keep things simple enough that the math is easy. in more advanced structural analysis, you start to figure out a little bit more about what's going on at the ends of the beams. Because here, remember, we had a pin, and that pin is where that 20 kips of force is. So the way that the force is spread out on the ends of the member, that's pretty complex. But as we get toward the middle of the member, the force spreads out and eventually becomes nice and uniform. All these little arrows, if we add them up, adds up to 20 kips of force. But that 20 kips of force is spread out over how many ever square inches we've got. Let's say, for example, this is, well, let's make it 4 inches by 5 inches. Now, literally, this is the most difficult thing we have to do in dealing with stresses. We have to be able to calculate areas. So if you're pretty comfortable calculating areas, you've got most of the tools you need to be able to handle structural or handle material analysis. We have some number of square inches of cross-sectional area here. The area is that of a rectangle, so it's length times width. 4 times 5 gives us 20 square inches. Our 20 kips of force is spread out over that 20 square inches. In the middle of the beam, that's a pretty good assumption that the force is spread out uniformly. It's a terrible assumption down here where the force is hooking onto a pin and the stresses here can look really weird. Down here in the middle, it's nice and uniform. So we have 20 kips of force spread out over 20 square inches. We can form a ratio out of that. We can take the ratio of the force, 20 kips, to the area, 20 square inches. Now, of course, 20 over 20, that's just 1. We have a kip per square inch. We have 1,000 pounds per square inch. So we have kips, I'll write it out here, kips per square inch. So in this situation here where I have this beam that has this relatively large cross-sectional area, 20 square inches, if it's supporting a load of 20 kips, that means that the material sees 1 kip on each square inch. That's what we'd see if we could zoom way in on this material, so far in that we really can't tell the area anymore. We could only say, well, there's 1 kip on each square inch. Now, those of you might be thinking ahead a little bit and have had some experience in some fluids or in other materials. You may recognize this as something we've dealt with before. We have a force divided by an area. Forces divided by areas are pressures. And a stress, in a sense, is a pressure. It's an internal pressure. Now, we're used to thinking about pressures as forces pushing on a structure. A pressure could be a pull also. Pressures can be in tension or they can be in compression. Stress is really just another name for material pressure. It's how the forces that are applied externally to a piece of material are resolved internally. Stresses are how much force is on each square inch. Now, because it's a special form of pressure and it's associated with the letter S for stress, we have a new letter for this. So let me write the equation down here. We've taken our force, this 20 kips, and we've divided it by the cross-sectional area, the number of square inches. That is what we call our normal stress. The word normal here doesn't mean regular or usual or everyday, the kind of ways we'd normally use the word normal, right? Normal is a fancy mathematical way of saying perpendicular. And the stresses when we're dealing with normal stress, we're considering forces that are perpendicular to this surface. Where we've cut this surface, the forces are at 90 degrees. So we call this normal stress. And the letter we use is that letter right there, which you may not recognize because it's a Greek letter. It's the Greek letter sigma. It's the small sigma. So sigma, sigma. It's the small sigma. We know the big sigma. Big sigma is our sum, our summation symbol. That's capital sigma. This is small sigma. Small sigma is the universal symbol for normal stress. And it's got the same equation that pressure had. It's force spread out over an area. Now, the force we figured out from truss analysis. We figured out how much force was on the member. What we didn't necessarily know was the area. And in fact, this is where design comes in. By changing the area, we change the stress. We don't change the force. The force is what needed to be held by that member to keep the structure in equilibrium. But the area is dependent on what we pick to support that load. If we decided here, for example, to go with a smaller beam, let's say we cut this thing in half, and instead of using 4 inches by 5 inches, we go with an area that is 2 inches by 5 inches. That's going to cut the area in half. The area is 2 times 5. That's going to be 10 square inches. In that case, our stress would no longer be 1 kip per square inch. We have force over area. So we're still applying 20 kips of force, but now it's spread out over a smaller number of square inches, 10 square inches. We get 2 kips per square inch. The less area there is, the higher the stress is. The more area there is, the lower the stress is. And that's an important idea because materials, real materials, have an upper limit, have several limits actually, on how much stress they can handle. We'll see this next week, but every material has 2 important factors to keep in mind for dealing with stress. One is what we call the yield stress, and the other is what we call the ultimate stress. The yield stress is the maximum amount of stress the material can handle and still go back to its original shape when we let it go. Think about bending a paper clip or using a paper clip. If you push it a little bit, it'll spring back to where it started with no problem. But if you push it too far, it will permanently change shape. It will yield. We also have ultimate stress. Ultimate stress is the maximum amount of stress the material can handle. And if we exceed that maximum stress, things break. In design, most often we try to stay away from the yield stress. We like things to be able to be stressed. We like to be able to load up structures, but we don't like them to permanently change shape. They can move, they can spring around a little bit, but we don't want them permanently changing shape. In some applications, we do purposely exceed the yield stress, but we don't want to go past the ultimate stress. So those are design factors. The area is what controls the stress that we're going to have, given an amount of force. The smaller the area, the bigger the stress. The bigger the area, the more our force is spread out, so the lower the stress. In fact, if we were to cut the area down to 1 square inch, if we put that same 20 kips of force, but over 1 square inch, we'd have 20 kips per square inch. That's a lot more stress. And that's getting up into the neighborhood of the maximum stresses of some materials. Some materials have maximum stresses in the usually tens of kips per square inch, can get up into hundreds or in some cases even thousands of kips per square inch. But tens, when you start thinking about loading 20,000 pounds on 1 square inch, you're probably pushing the material pretty hard. One thing that hopefully we'll come away with in dealing with this part of the course is just how robust a lot of the systems we have are out there. We're using materials that can handle way more stress than what we're putting on them. The kinds of things that we'd never really have to worry about. Like when you're using an engine hoist, you look at the material that we're using in that engine hoist. It's way underloaded. I mean, we're lifting 1,000 pounds with it, 2,000 pounds with it. We need 20,000 pounds on a square inch to break it. So it's not the kind of thing that tends to fail easily, unless it's damaged, unless it's had something that's compromised the strength of that material. So that's our definition of normal stress. Normal stress is force spread out over an area. Now, at this point, I'm assuming you know how to find the forces. You know how to do truss analysis. You can figure out how much force there is on a member. So we're not going to focus on that from this point forward. Instead, you mostly have to find the areas and figure out what the stresses are, and then eventually figure out, well, is that acceptable? Is that stress safe for the material that we want to use in this application? That's the idea behind normal stress. Now, one thing before we go back here to the slides, the units here, we're dealing with kips per square inch, but that could just as easily be pounds per square inch. And if you remember a pound per square inch, most of you have been through the A&P program, know that the pounds per square inch can be written in kind of a shorthand as PSI, pounds per square inch. When we've got kips per square inch, we can abbreviate that as KSI. A KSI is 1,000 PSI. It's a kilo PSI. So it's 1,000 pounds per square inch. And in fact, in some applications, we even get to what we call MIPS, millions of pounds per square inch. That's what we call an MSI. MSI stands for millions of pounds per square inch. So depending on the material, we start talking about things like titanium and such, we can get up into stresses that are millions of pounds per square inch. But those are the three units we tend to use for stress: PSI, KSI, or MSI. And the biggest thing to keep in mind is that some calculations will require you to put your units into PSI. So if you've done all your calculations in KSI, you'd have to tack on an extra 3 zeros if you need to use PSI. But I'll show you those when we get there. So let's see here. So that's the idea of stress. So if we cut the beam and we zoom in on it, the forces that are applied look like they're uniformly distributed. When forces are uniformly spread out over an area, we have a pressure. And that pressure we call stress, normal stress specifically. So sigma is the force over the area. And that's the first big equation to keep in mind for this section. So if you can find a force, you can calculate an area, it's not too hard to figure out the normal stress. Now, stress is the internal view of force. It's what the molecules inside the material feel. If we zoomed in so close to the material that we can't see the structure, instead we can just see the atoms and the molecules that make it up, the stress is what we'd physically see. So stress is what we call a material equivalent of force. It tells us how much force acts on each square inch. And it simplifies things quite a bit because it actually removes the details of the shape and how it's loaded. When we found our stress a few minutes ago, we divided by the shape. Essentially, we divided by the area. When you divide by things, you lose them. You divide, think about solving an algebraic equation. You divide by a coefficient, that coefficient goes away. You lose the information. When we divide our force, which is an external force, it's something on the large scale in the physical picture, external to the material, we divide that by the shape of the material, by the area, we get an internal quantity. We jump into the material and get the stress. We've removed the details of what that shape is. It doesn't matter whether the 10 square inches was rectangular or circular or an angle, triangle. It doesn't make any difference. As long as it added up to 10 square inches, we've got this amount of stress. That's a huge simplification, because if we didn't have that, think about the world we'd be in if we didn't have that simplification. It would mean that I'd have to have a big catalog somewhere of every possible shape of a beam made out of a certain material. Let's say aluminum, for example. Let's restrict ourselves to aluminum for the moment. I'd have to have a big catalog somewhere that says, well, if it's shaped like this, like a triangle, it can handle this amount of force. If it's a rectangle with these dimensions, it can handle this amount of force. If it's circular, it can handle this amount of force with this inside and outside diameter. You'd have to have an infinite number. This book would be huge with all these different properties for each of the different possible beams. What stress lets us do is eliminate all of that and basically come up with one number. If this material is made out of 2024 T6 aluminum, then it can handle 35 KSI before it breaks. And I'm making up the numbers, so please don't check me on that. But we'll get to some numbers later. But it doesn't matter what the size and shape of the beam are. If we can use those external values, the force and the area, when we divide those, we get an internal value. We get something that applies just to the material. So all we ever have to compare it against is properties of that material, not any particular beam. That is a huge simplification. It reduces essentially an infinite space down to one number. And so that's a huge simplification and really, really important. So it lets us focus on the material instead of that specific member. And makes it easy to swap out materials. We can say, well, if I'm stuck with this 10 square inch area, I know my stress is going to be 2 KSI. What material can I make this out of? So you go to a big table that lists all the different materials and what their ultimate stresses are. And you can find out, okay, well, wood's not going to work for me. So our southern yellow pine isn't going to do the job. So I'm going to have to go maybe to aluminum. Well, what aluminum can I easily get? Or maybe steel, maybe magnesium, and so on. We just can focus on the material and not that specific member. So that's a big simplification, makes design a lot easier. Now, that's stress. But stress is only half of the story. When a stress is applied, when you apply a force to something, you get a response. The material reacts to the force. Think again about, say, bending a paperclip. You apply a force, and in reaction, the paperclip moves. Maybe moves far enough to not be able to spring back. The material changes shape. All materials do this to a certain extent. When we apply a force to it, the shape changes. If we apply a tensile force, most materials increase in size. When we apply a compressive force, they shrink. Now, it may be very, very small. We might be talking about thousandths or even millionths of an inch, but it's a reaction. That reaction to stress, the change in shape of a material, or what we call the deformation of the material, change in shape. That's the fancy material word for change in shape, is deformation. It deforms, maybe not permanently, but it will change its shape. Strain is what we call that change in shape. We call that deformation. Strain is a measure of the response to stress, the response of a material to stress. And just like stress, it's an internal value. It's not something that we'd have measured out, for example, in inches, because inches is a physical measurement that requires that we measure something on the outside. Instead, what strain tells us is how much each inch grows. It's a ratio. It says that each inch is going to become a thousandth of an inch bigger. So that way I know if I've got something that is 20 inches long, I can predict how much longer overall it's going to grow. If it's 6 inches long, I've got the same ratio. Each inch grows by 1,000th of an inch. Strain is a reaction to stress, but it's the material's reaction to stress. We can add that up and get the overall deformation. That's one of the things we'll do is figure out if we've got a 20-foot long piece of material and we apply force to it, how much bigger does it get? But to find that, we first need to find the internal values, the strain, how much each inch grows or shrinks if we're dealing in compression. And the basic principle is that all materials behave essentially like springs. When you pull on them, they stretch. When you push on them, they shrink. It just happens to be so small that we normally can't observe it unless you're dealing with something that is intended to change its shape a lot, like a spring. Generally, we don't see that change in shape very easily, but it can be measured. We might need a micrometer to measure it, but it can be measured. And there is with most materials, a relatively simple relationship. As long as you don't push it too hard or pull it too hard, there's a relatively simple relationship between the force and deformation. We call that Hooke's law. Those of you that have studied a little bit of physics before may have come across Hooke's law before. Hooke's law was your spring law. It was what said the force and the distance, the extension or the compression of the spring were proportional. F equals kx, for example. We've got a similar kind of idea with most materials because the bonds between atoms and molecules act kind of spring-like. They're electromagnetic in nature, and that electromagnetism has sort of a linear response to it as long as you don't push things too hard. Now, as you start getting up toward the limits of the material, Hooke's law breaks down. Hooke's law does not work, just like Ohm's law doesn't work when you push things too hard. Ohm's law is a very, very similar kind of rule to Hooke's law. Hooke's law says you've got a nice proportional relationship between force and shape. That proportionality is dependent on the material. Ohm's law said kind of the same thing between voltage and current, that there's a proportionality there. That proportionality we call resistance. And that works as long as you don't push things too hard. Hopefully in your electrical class, one of the demonstrations I used to run, and hopefully that was something that you got, was you saw what happens if you turn the voltages up too high and how much current flows, and the fact that whatever we're dealing with tends to burst into flames. Fire is not in Ohm's law, and braking is not in Hooke's law. So when you start pushing things too far, Hooke's law stops working. But we'll see that as long as we stay below certain limits, Hooke's law works great. And we've designed most of our materials and most of our structures to keep within the range where Hooke's law works because it is simple and easy to deal with. So Hooke's law says that the change in size, how much deformation we get, is proportional to the force applied. So if we double the force, we get twice the extension or twice the compression. If we double the stress, we get twice the strain. If we quadruple the stress, we get 4 times the strain. So stress and strain are proportional to each other. Now here's the picture. Up on the top, I've got this rectangular beam that is not loaded. That unloaded beam is at what we could call its rest length, and I've labeled that L. L is the length of the beam without any load applied to it. When we apply a load, and that's what's shown in the bottom picture is the beam under stress. And when that beam is loaded, it stretches out. It stretches out by an amount that's small, even though it's exaggerated in the drawing. This little funny looking letter here is another Greek letter, what we call delta. This is the small delta. Capital delta is the triangle. This is the small delta, and it's usually used to represent a very small change in something. So it looks like kind of a curled over, like somebody squished the staff on the D. So it's a little curly D-shaped letter. That's the extension, or what we could call the elongation of the beam, the deformation of the beam, how much it grew. Well, if we take that elongation and we spread it out over the length. Let's say, for example, this elongation is 10 thousandths of an inch, so 0.010 inches. If this thing is 5 inches long, then that means that each inch grew by 2 thousandths. If we spread the elongation out over the rest length, we get an idea of how much each inch grows. That's a material idea. That tells us no matter how many inches this has, each inch grows by 2 thousandths of an inch. And that would let us predict for any length of the beam how much it's going to elongate. If each inch grows by 2 thousandths of an inch, then if we've got 100 inches, then we're going to have then we'll have 2/10ths of an inch of elongation. So the amount of elongation spread out over the length gives us a material measurement of deformation, and that's what we call strain. Strain is what we get when we spread out the elongation over the length of the beam. So switching over here to the, let's see, there we go. Switching over here. If we have an elongation, delta, and we spread that out over the length, and mathematically spreading something out, it's dividing, we get a measurement that we call the strain. And the strain uses this funny looking little letter, sort of a curly E. We call that epsilon. This one up here is delta. In math, epsilon and delta are used very frequently to represent small quantities. For those of you who might have studied a little bit of calculus or something like that, you might have become familiar with epsilons and deltas. And they're used here for that same kind of reason. These tend to be very small values. The total amount of elongation, so delta is the elongation. It's how much stretch or shrink we've got. Stretch if we're in tension, shrink if we're in compression. That's actually measured in inches, typically. Usually fractions of an inch, thousandths of an inch, or lower, millionths of an inch. Elongation is the physical amount of change in shape. If we spread that out over the length, we get epsilon, we get our strain. So strain is the material deformation. You can think of it as how much each inch grows or shrinks. Now, in fact, if we look at the units on it, delta is typically in inches. The length is typically in inches. If we've got the same units in the top and the bottom, they cancel out. Epsilon, the strain, is dimensionless. It's a ratio. Now, sometimes people like to say it's inches per inch, which is kind of a weird thing to say. Say, well, it's a measure of inches per inch. But if you think about what that means, what it's really telling you is when you say inches per inch, it means how many inches did each inch grow, or how many inches did each inch shrink. The top inches is how much change there was. The bottom is referencing 1 inch. And typically in engineering in the U.S., we tend to stick with inches. That is a bit of a concern when we're dealing with calculating this, because if you aren't careful about your units, you might have a length in feet, for example. You got to make sure you convert your units to inches in order for this to work out. So be careful of that. There's a little bit of unit problem here that can come up. So you'd want to be careful about that. and we'll practice with it a bit. But that's strain. Strain is the amount of deformation that we get, but on a material level. How many inches each inch grows or how many inches each inch shrinks. We can add that up and figure out how much overall elongation, or another word would be deformation, how much elongation or how much deformation that we get. Now, how it typically works with materials is that we can predict the strain from the stress. Now, that prediction is experimental. People figured it out based on actually testing materials. We don't have a good enough material science theory yet to be able to come up with some description of the material internally and predict all of its values, all of its properties from that theory. We are limited today to experiment. So if we want to know what the relationship is between stress and strain for a particular material, our only choice is to go and take that material and put load on it and measure how much it stretches, and then figure out what that relationship needs to be between stress and strain. It's determined entirely experimentally, and it's not done just once. They might take 1,000 samples of the same material and test it repeatedly and then average the results together. And that's practically what's done today. Now, maybe someday someone will come up with a good enough molecular theory of materials to be able to predict that from that theory, but we're not there yet. So those are our two big equations here for materials. So the big takeaways from tonight, we've got normal stress, which is sigma equals force over area, with units of things like PSI, KSI, or MSI. As long as you can figure out areas in square inches, you can figure out stresses. And then we have normal strain, because the direction of change in length is perpendicular to the cross section. So we call it normal strain. Strain is elongation over length. And it is dimensionless, or inches per inch is pretty typical to use for that. So those are our two big equations at this point. Now, typically, we can measure the external values here. We can measure forces, we can measure areas, we can measure elongation, we can measure the length. The stress and the strain, sigma and epsilon, those are the material properties. And those are what are related in things like references. References for a particular material will tell us if we put a certain amount of stress on a material, we'll get this amount of strain. And then from that strain, we can predict what happens to the material, how much it grows or how much it shrinks. In fact, I can show you a little drawing here that in a minute that relates all of these values and how we typically use them. But let's jump back to the slides here for just a bit. So let's see, there we are. So there's our equation for strain. Strain epsilon is delta, the elongation or the deformation, over the length. So strain is a measure of material deformation or relative deformation. It's how much each unit of length has increased or decreased as a result of applying stress. So we squeeze on something, it shrinks. If we spread that amount of shrink out over the entire length, we have the strain. If we pull on something, it stretches. If we spread that stretch out over the entire length, we get our strain. Strain is how much the material itself increases or decreases in length. So it's the stretch or the shrink spread out over the length of that member. It's a material quantity. It doesn't refer to the geometry or the size of the member anymore. Length is divided out. In fact, we've got all those geometric factors, area and length. Those are all divided out. We're factoring them out of these values by dividing them. And that's what gives us our internal picture, our internal values. Now, stress and strain are related to each other. Stress causes strain. We can predict from experiments that people have done, when you apply stresses, you'll get a certain response from the material in terms of the strain. Stresses induce strain. Stresses cause strain. Never goes the other way around. Something doesn't change shape first and then put a force on it. You put the force on, the material responds. You release the force, the material responds again. So stresses cause strain. There is a constant between the two. There's a constant between the two that connects the stress and the strain, just like resistance connects voltage and current. What we call the modulus of elasticity, or Young's modulus, connects stress and strain. That's Hooke's law. Hooke's law's proportionality is the modulus of elasticity, that constant that connects the two sides together. And the equation looks something like this. So on the left, we've got stress. On the right, we've got strain with the little e, the little epsilon. And then that capital E is the modulus of elasticity. That's like the resistance. If you replace this equation with Ohm's law, you'd have voltage equals resistance times current. You'd have your E equals IR, or your V equals IR, however you do it. That constant is all about the material. And that constant does change with the material. Some materials have a very large modulus of elasticity. Others have a very small modulus. It changes the response between stress and strain. And one of the things we can take a look at here with the modulus is that it has to be a very large number. So we have Hooke's law. That's the next big equation. And that says that stress equals the Young's modulus, or modulus of elasticity, times the strain. Now the strain is typically a very small number, usually thousandths of inch or inches or millionths of inch per inch. Very small number. Stress is usually pretty big. Thousands of pounds per square inch, millions of pounds per square inch. To get a big number out of a small number and do multiplication with it, whatever you multiply by must be very big. So typically, E is a big number. The modulus of elasticity is a big number. And it becomes a little clearer if we turn this equation around, because this isn't how we'd actually use the equation. Normally, we know what stress is applied to a member. We can figure that out from the force and the area. We can figure out the stress. We want to figure out what the strain is. And one of the ways we can get the strain from Hooke's law is to solve the equation for epsilon. And to do that, we'd have to divide both sides by E. And if I flip this around so it's a little clearer, I have strain is stress divided by the Young's modulus. So we take that stress and we divide it by a really big number. That's what gives us the small amount of strain. So you can actually attach different values of the Young's modulus to different materials. If you have, for example, a very stiff material, a material that doesn't change size very much, what is a very rigid material, then its Young's modulus is very big, because in order to get any kind of strain out of it, in order to get any kind of change in shape, you're going to have to apply lots and lots and lots of stress. On the other hand, if we have a very flexible material, a very what we could call plastic material, in a plastic material that can stretch very easily, that changes its shape very easily, the modulus is a lot lower. because it doesn't take as much stress to get a significant amount of strain. So the Young's modulus is a material property. And if we look at all the values we've got here, we can basically divide them into material properties and um, essentially internal and external properties. We have our internal properties, which only depend on the material. That would be things like stress, strain, and the Young's modulus. Those are all depend only on the material. Then we have these external values, or the physical values. The external picture, what we see, what we can actually measure. We've got force, we've got our elongation, and we've got geometry. We've got area and length. Those are all in the outside picture. They're things we can measure from the outside. The internal picture is all about the material. And because it's simpler to figure out the values with respect to the material, typically we follow this procedure where we start with the external values. We calculate the internal ones. We usually start with calculating the stress. From the stress and the Young's modulus, we can figure out strain. And then from strain, we can figure out the deformation. It's easier to express the relationship between stress and strain in terms of these material properties. But what we want at the end of the day is something we can physically measure. We want to know, how much bigger is this beam going to get? Is this going to stretch out by 2 inches, by 10 inches, by a thousandth of an inch? Those are physical external properties that we need. But the calculations are a lot easier on the material level. The references are a lot easier on the material level. So we start out here in the physical world, we jump into the material, we do our calculations there, and then we jump back out. And I always draw up this little picture to kind of illustrate that, to illustrate the way we would solve a typical problem with materials. I'll try to keep this all on the same page here, or at least on the same screen. So there are properties. Typically, we start out here with a force. That's the load that we have calculated based on doing our truss analysis, for example. We figured out that there's some amount of force on that material, on that beam. If we use the area, we can define the stress. Stress was force divided by area. So we can jump over here to get the stress by using the area, because stress is force divided by area. So if we start with the force, we divide it by area to get our stress. Now from stress, we can get down here to strain by using Young's modulus. Strain is stress divided by Young's modulus. That's a material property. So we can go to a manual and look up what E is for a particular piece of material. All this over here is the material side. Stress, Young's modulus, and strain. Those three values right there. What we want is over here in the physical world. Forces, lengths, things like that. We can get over here to our elongation by using strain. The definition of strain was that strain was the deformation over the length. If we cross multiply that out, we get that the deformation is the strain times the length. The strain tells us how much each inch grows by. The length tells us how many inches we're dealing with. So we get our elongation. So it's length that connects strain and deformation. So we get over here to our physical deformation, the amount of change in length. That's the typical process we follow. We start with a force. We know that force is spread out over some area, the cross-sectional area of the member. That gives us our stress. We can look up, based on the material, the Young's modulus and figure out the strain, how much each inch deforms. Then we can multiply that by the length and get what our overall growth is. Now, there is a way to jump straight to that goal here from the force to the length, to the change in length, but it requires plugging all these equations together. And that there's an equation for it. We'll look at it later, but at this point, I really prefer to just take the individual small steps to keep familiar and get familiar with these new ideas. We don't want to just find an equation we can just plug a bunch of stuff into, because it does lead to some problems that we'll get into a little later. But we'll try an example here so that you can see how this all works together. Anyone have any questions so far? All right, so let's try an example here. Let's see, do I have one in the notes? So that's stress and strain. Young's modulus, pretty big number. So it takes a lot of stress to get even a little bit of strain. Normal stresses, we already talked about that, perpendicular. So let's try an example. So let's, using this picture here, let's take a beam and we'll put a load on it. Let's put 10 kips on it. Now, the first thing I want to note here, sometimes people go off on a tangent here. You've got 10 kips on one side, 10 kips on the other. And so they say the force on the member is 20 kips. Don't make that mistake. It's easy to kind of jump that way if you're trying to go quickly. But remember that this 10 kips over here is actually counteracting this 10 kips here. That's what's keeping this in equilibrium. It doesn't mean the middle of the beam feels like it's being pulled on by 20 kips. If you cut the beam in half, whichever half you're keeping, you're still going to have to grab onto it with 10 kips of force. That means there's 10 kips of force inside this beam. Now, in order to figure out the stress and to do the calculations here, we need some information. We need some information we haven't needed before. We need something about the cross-sectional area. We need something about the length, and we need to know the Young's modulus. We need to know the material. These two factors are geometry. Area and length are the physical size and shape of that beam. The Young's modulus is about the material. So let's say we pick a material that has a Young's modulus of 5 MSI. That would be 5 million pounds per square inch. Usually the Young's modulus is a very big number, millions, thousands. We have to be careful about units and what units we're plugging together. So we might have to use this, instead of saying it's 5 million pounds per square inch, we might have to say it's 5,000 KSI, or it's 5 million, get enough zeros there, PSI. Which one you use, you select based on the force that you're using. If you're using kips, make sure your stresses and your modulus is in KSI. If you're using pounds, use PSI. Usually we don't put millions of pounds on a structure, so usually it's only kips or PS or pounds. But be careful, that it's an easy way to get off by a factor of 1,000, and that kind of matters. So make sure you use the same units on your Young's modulus that you use with the material, with the forces. Now we need an area and a length. On most problems, you'll have to figure out the area. They will say, well, the cross section is a square with 2 inches on the side. So that's this one here. Be careful about that. Make sure you know how to calculate your areas. So you've got 2 inches on each side here. So the area is 4 square inches. Now, where this gets a little more challenging is when we have, say, a hollow beam. So you're going to have to learn how to and know how to calculate areas of hollow structures. And we'll do an example of that in the practicum session. Tonight we'll do a circular and we'll do a rectangular hollow beam and see how that changes things. Now the area is 4 square inches here, and I'm just going to arbitrarily say the length of this is, let's say, 6 feet long. So it's a 6-foot long beam. It's got a cross-sectional area of 4 square inches, and whatever material this is has a modulus of 5 MSI. With that information, we can do a trip around the circle here. We start with our force. We've got 10 kips. Using the area, we can find the stress. So stress is force over area. And the amount of stress, we've got 10 kips over 4 square inches. So we've got 10 divided by 4, that's 2.5 kips per square inch, or KSI. Now, one of the reasons I like doing it this way is because right here is a good point to check what you're doing and make sure that what you're working on isn't going to break. If this is what you're doing as part of design, you're saying you've done your truss analysis and you've figured out that this member has to carry 10 kips of force, 10,000 pounds, and you're trying different things to figure out what material or what shape of beam you should go with. If you jump right from force to elongation, you might miss some important things over on this side. Specifically, you might miss limits. If I've done this calculation and I found my stress is 2.5 KSI, that gives me an opportunity to check and make sure that that's a reasonable amount of stress to have on this material. If this material is wood, is southern yellow pine, maybe 2.5 KSI is too much, and this thing's going to break. If that's above its ultimate stress, I can't use that material. And people have gotten themselves into trouble. People have caused accidents, and people have lost their lives because of calculations like this, where somebody did the shortcut calculation and didn't recognize that the stress they were going to put in that material was much higher than what the amount of stress that material could handle was. And they start loading the structure up and it starts to break. And that becomes a problem. So whenever you calculate a stress in a material, always take a pause right there and say, well, how does that compare to the maximum stress I can put on the material, what the limits are on that stress? And if it's anywhere nearby, you might want to consider going with something else. Maybe 4 square inches is too small and I've got to go to something bigger. Or maybe my material is too weak and I need to go to a stronger material. But it's a point in design that really can't be skipped over. So here we're going to assume, because we don't know what the limits are on this material, that 2.5 KSI is fine. So we've got our stress. So we're here now. We've got our stress. We need to figure out our strain, how much each inch is going to grow. Well, strain is stress divided by elongation. So we have a stress of, we got to pick the right units here, because remember, strain has to be dimensionless. The units have to cancel out. If I put 5 MSI and then 2.5 KSI in, I've got a mismatch in between my units. You're always going to go with the prefix that matches your force. So I've got 5,000, I've got, 2.5 KSI. That's my stress. I'm going to divide that by 5,000 KSI. There, the units cancel out. And I've got 2.5 divided by 5,000. And I'm going to the calculator to make sure I don't screw up the number of zeros in that. So 2.5 divided by 5,000. We've got 0.0005. Now that's dimensionless. It means that, for example, each inch grows by 0.0005 inches. But you could throw any units on it that you want. In fact, that's part of the beauty of dimensionless ratios, is that you can put any units you want on it. So I could say, for example, well, each inch will grow by 0.0005 inches. Each foot will also grow by 0.0005 feet. Each meter would grow by 0.0005 meters. That's one of those things you can do with a ratio. So I don't have to worry so much about my length units. The length units here will give me my final answers units. If I plug in feet, I'm going to get feet out. If I plug in inches, I'll get inches out. Be careful of that. If a problem asks you, for example, what is the elongation in inches, and you go and find the elongation in feet, you've got a units problem. But we can always do that. The elongation will inherit the units of length. So let's figure out our elongation here. We'll go from this equation. The elongation is the strain, how much each unit of length grows, by how many units of length we've got. So elongation is our strain, 0.0005, times the length, 6 feet. And when I multiply that out, I get 0.003 feet. Now, that's not a very instructive or easy number to really keep in your head. I don't know offhand how big 0.003 feet is, so it might be worth turning it into inches. You can do that unit conversion. Just have to multiply it by 12, and it gives us a little bit better idea, 0.036 inches, if we multiply that by 12. Now, 36 thousandths of an inch, that's about a 32nd of an inch. It's about 1/32. So that gives us a little bit better idea of what we're dealing with here. So with this beam made out of whatever material has 5,000 KSI of Young's modulus, a 6-foot long beam, when I load that up with 10,000 pounds, it'll grow by a 32nd of an inch. That's not too bad. So that's a pretty reasonable material to be working with. You do have another opportunity for a check here. If this ends up being thousandths of an inch, you're probably okay. If it ends up being inches, you might want to worry. If this thing is only a few feet long and it grows by 1, 2, 3 inches, I'd start to be worried that I'm really pushing the limits of the material and this isn't a good model anymore. I've kind of broken things by pushing it too hard. Usually you get fractions of an inch, small fractions of an inch, even in fairly long structures. Now, if this thing was 100 feet long, I probably wouldn't worry too much about an inch or two of growth. But at 6 feet, I shouldn't be seeing inches with reasonable materials. So that's how this stuff works. We figure out our stresses from geometry and force. We figure out our strain from the relationship between stress and strain and the material involved, that Young's modulus. And then we figure out our elongation. We jump back into the physical world by using the length and the strain telling us the ratio of the elongation to the length. So that's the content here for this evening. In our practicum session, I'll do a couple more examples of these to give you a chance to work out a couple of these with some different cross sections and see how that reacts in stress and in strain and overall elongation. And then next time, we'll take a look at the shear equivalent of these ideas. Here we've looked at normal stresses, which are pulls and pushes. That's the force that members experienced in trusses. But if we look at the pins in the truss, those all had shear loads on them. They were trying to cut through the diameter or cut through that cross-sectional area. That's a shear stress. And so we'll look at shear stress and shear strain. So that's the content here for the evening. Anyone have any questions so far?
Nope.
All right. Well, oh, there we go. If you are hanging around, then come back in about 10 minutes or so. We'll work a couple more problems out. I'll give you a chance to work with a couple of them. But if you're departing, well, have a good evening, and I will see you Wednesday night.